Okay, so today in class we learned a lot about the different ways that populations can evolve, aside from the pressures that predators, limited food, sexual selection put on them. We have gene flow, we have bottleneck, founder effect, all of that good stuff. Um, so I want you to recall that evolution is any change in the frequency of an allele in a population's gene pool. And so if we want to find out if a population is evolving, we'd want to find out what the frequency of an allele is to see if that frequency is changing. All right, and so this is what two guys named Hardy and Weinberg were thinking about, and they created the Hardy-Weinberg principle, which is that populations are in equilibrium, which is kind of the opposite of evolution, if they meet certain conditions. So remember, equilibrium is a state of balance in which there's no overall change, so the frequencies will not be changing, although it may be dynamic, which includes some variation within a limited range. All right, so there's a few conditions for equilibrium to exist. The first is that you have a large population and everyone in the population breeds. The second is that you have random mating, so not too picky. If you look at this nice little personal ad by this rabbit, single gray female looking for male rabbit, any age, any body type, any fur color, long walks on the beach optional. Pretty much don't care. So this would not be true of, say, the human population. Next one is there's no immigration or emigration. So there's no genes entering the population and nothing's leaving. And the last is that there's no natural selection. So there's none of these other pressures of climate change, predators, etc. that are working on this population. So how do we know? We use an equation because frequency is math and we're going to do math. So p squared plus 2pq plus q squared equals 1 is the Hardy-Weinberg equation. In this case, p squared is the percent of homozygous individuals, and they're homozygous dominant. Remember, big A is dominant. Any capital letters are dominant. 2pq is the percent of heterozygous individuals, and q squared is the percent of homozygous recessive individuals. All right, so how do we derive it? We take p squared plus 2pq plus q squared equals 1, and it derives from an original equation of p plus q equals 1, in which p is the percent of dominant alleles present in the population, and q is the percent of recessive alleles present in the population. Take our original equation, p plus q equals 1. We square both sides. We expand this out, so we know that 1 squared is 1. And then p plus q times p plus q. We use FOIL, first, outer, inner, last, and multiply this out. We get p squared plus pq plus pq plus q squared equals 1. We simplify that down, combining the two pq's. All right, so that's the math part. So how does this work? First, you want to calculate p and q. Then some time and generations pass. You calculate p and q again, and you repeat because science works best with you have more data. So if p and q values change, then evolution is occurring. If your p and q values stay constant, then your population is in equilibrium. All right. So to calculate p and q, you use the percent of recessive phenotypes to calculate q, because remember, if you have a recessive phenotype, you know the genotype has to be homozygous recessive. Then we use p plus q equals 1 to find q. And then if perhaps you're looking for the percent of heterozygotes, you can use 2pq. So if you remember, like sickle cell anemia, heterozygotes had this whole other special thing happening, so you might want to know how many of those are in a population. All right, next up. So suppose you discover an island of cats. 455 cats have dark hair, so you know, since dark hair is dominant to light hair, that their genotype is either big D or big D little d. 45 cats have light hair, so their genotype is definitely little d for 500 total cats. We know that q squared equals percent dd. So q squared equals 45 out of 500. Therefore, q squared equals 0.09. So now that we know that q squared is 0.09, we make the square root of both sides, and we get that q equals 0.3. Recall that p plus q equals 1. Therefore, p plus 0.3 equals 1, so p equals 0.7. If we want to know how many cats are homozygous dominant, we can say, okay, p squared is 0.7 squared, so that's 49%. We want to know how many are heterozygous. 2 times P times Q equals 42%. And we can always check our work by saying, okay, 42% plus 49% plus 9%. Good, that equals 100%. Doesn't add up to 100%. We might be in trouble. All right, so we come back to this island of cats again, and we find that there's a lot of cats. A few years later, they've been breeding. We find 820 cats with dark hair, 180 cats with light hair, and 2,000 total cats. So Q squared equals 180 divided by 2,000. So Q squared equals 0.09. Therefore, Q equals 0.3, P equals 0.7, and the population's in equilibrium. Now suppose that we found 320 light-haired cats and 1,680 dark-haired cats. Alright, so in this case, Q squared would be 320 out of 2,000, and that would be 0.16, so Q would be 0.4. Square root of 0.16 is 0.4. And then P plus 0.4 equals 1, so P is 6. Now clearly, this are different numbers than these guys, so evolution is occurring. Alright. So let's do a practice problem. Scientists working in a lab with mice accidentally lost a group of them. However, they did know some information about the original group. A few months later, a new grad student found a population of white mice living in an abandoned lab down the hall. She observed and counted them. She brought them back to her lab and raised them for several more generations, doing occasional breeding experiments with them, but otherwise letting them live and breed together. Before she left for the summer, she took another census. Here's her data. So the mice that had only white fur are recessive, and the mice that had some dark fur are dominant. So they have big D, or big D, little d. Alright, so the original group had 75 mice with some dark fur and 25 mice with only white fur. The group that she found in the lab had 168 with some dark fur and 32 with only white fur. And after the experiments, she found that she had 420 with some dark fur and 80 with only white fur. So use the Hardy-Weinberg equations to determine if the population remained in equilibrium after escaping from the lab, so from the original group to the abandoned lab group, and then from the abandoned lab group to after the student completed the experiments. You can do that on your worksheet. Alright, your next mission is to find out if your rhesus positive or negative if you can. So the rhesus factor is the part of your blood type that isn't A, B, or O. For example, I have A positive blood, so that means that my rhesus factor is plus or positive. If you can't find out your blood type, you just don't know it, then go ahead and just pick whether you'd like to be positive or negative and write it down on your worksheet. 15% of the USA is Rh negative, so we're going to figure out what our class is and if we're, in equilibrium with the rest of the country. Okay, thanks. Have a good night.